Welcome to the Soil Sistas channel. Here's the next installment of weekly recaps for the Intro Soil Science class. The exam on Thursday, October 20th covers lectures 1 through 7. You do need a Scantron, so come prepared. Also, you should be working on your homework 2 assignment, which should help you prepare for this exam. This assignment is due Tuesday, October 18th at 8:10 a.m. and should be completed on a Scantron. Don't be late. Here's a list of keywords covered during week 3, lectures 6 and 7. Please note, not all necessary keywords are listed, so please look over your material.
This week in lecture we covered bulk density and particle density. Here we'll discuss a little bit of the difference between the two since they're very similar. So bulk density is described as rho subscript B, and particle density is rho subscript S, S standing for solids. So the equation for bulk density is the mass over the volume of the solids and pore space. And for particle density, you're only accounting for the volume of the solids. So here in an example, the bulk density would be taking the entire aggregate or the whole unit of soil, the volume representing the amount of the solids, which are the soil particles, the air, and water, where the particle density is only accounting for the solids. So if you look back here, the volume of solids in the pore space is going to be greater than the volume of the solids alone. So dividing by a bigger number here is going to give you a smaller bulk density value. Where here, dividing by a smaller number gives you a bigger value for your particle density.
So this is a pie chart of the components of the soil, and this is just a rough estimate, but typically you see a 50% makeup of mineral matter and then organic matter. The other 50% is water and air, and these two components are what makes porosity. So this is percent porosity, and then the percent of water and air varies with the water content. So looking at water content, you can measure it in 2 different ways. One is gravimetric water content, which is the mass of water over the mass of dry soil. And this is easy to obtain. You just first weigh the soil and get that reading, and then you can oven dry it and get the mass of the dry soil. The next is volumetric water content, which is the volume of water over the volume of soil. And then to convert between gravimetric and volumetric water content, you need to know the density, the bulk density, and you also need to know the density of water. But since the density of water is just 1, then you don't have to account for it. Water potential is the movement of water. And we look at water potential with these 3 different potentials. So gravimetric potential is the movement of water by gravity. So if you think about water moving down from the top of a hill to the bottom of a hill, where it has the most potential is at the top of the hill. And then matrix potential is the movement of water into soil by capillary action, and therefore it's negative. Osmotic potential is the difference of solute concentrations. So if you have a system where one side has a higher concentration of solutes than the other side, you'll see a movement of water to the higher concentration of solutes. And then total water potential is the sum of all of these potentials, but you want to keep in mind that matrix potential is always negative or 0. And when matrix potential is 0, that's when you know that the soil is saturated.
Here we're going to give an example as shown in class relating gravimetric and matrix potential. So let's take this sponge here and pretend it's our saturated soil. So we're going to saturate it, and here we have, because it's not draining, we have the gravimetric potential and the matrix potential equaling each other. So the matrix potential is the ability for the soil to hold on to those water molecules, and the gravitational potential is the amount of force due to gravity that's pushing down on that water. But since it's not draining, they're equal to each other. However, if we change the gravitational potential, the soil will begin to drain. In this example, we start with the sponge on its side with an initial gravimetric potential of 5 centimeters. When the sponge is rotated, an additional 15 centimeters is added, thus making the soil drain. So here the matrix potential is no longer counteracting the gravimetric potential, so it drains. Here we have a water retention curve. A water retention curve relates matrix potential, which is on the x-axis, to water content on the y-axis. To begin, we start with a saturated soil with a matrix potential of 0. As water content decreases, the ability for soil to hold onto water molecules decreases. The initial draining of water from soil is the draining of the gravitational water. Once the soil reaches the field capacity, which is the amount of soil moisture or water content held in the soil after excess water has drained away, the rate of downward movement decreases, and the water in the soil is the available water for plants to use. Once the available water is no longer in abundance, the soil has reached the wilting point, where the plants cannot exert enough force to take in the small amount of water left in the soil.